Why 80 characters? Why were the punch cards 80 characters? Well, the answer is it was an upgrade from the 45-column punch card. The 80-character card was introduced in 1928, so it was a natural thing to use when they first created computers.
For the final talk, we've got Dan Vanderkam. Dan, let's give him a round of applause. Now, Dan, he is the author of Effective TypeScript, and he's also an independent software developer. And I asked him for an interesting fact, and he says that he has a pond, but it has no fish in it, only 4 frogs. So since we're in an aquarium, we're going to check his pockets before we leave. But other than that, let's take it away, Dan.
All right, thank you. Great. All right, yeah. So last talk of the day, we're almost there. This talk is going to be a little bit different. This is going to be a very high level. So we've dived deep into a lot of I guess trenches. Is that what they are in an ocean today? But today, for this talk, we're going to be very high level. We're going to talk about why we use plain text to represent something as complicated as computer code. So, just a little bit about me quickly. So, yeah, like Nick mentioned, I have a O'Reilly book and I blog at effectivetypescript.com. I also like to do rock climbing, and I'm also gotten pretty into birding. This is a Victoria's rifle bird that's hanging out on my shoulder. I liked birds until maybe the lunch today made me question it when one of those gulls swooped in and rudely stole half of my lobster roll. Yeah, so I don't know. I might have to change the cover of the next edition of Effective TypeScript. But yeah, like Nick said, I'm independent now, but formerly I was at Google and Sidewalk Labs. So, all right, we're all developers, right? Let's make a computer program. Maybe we can do something fun like sort a list of numbers. So what's the first thing we're going to do? Fire up our UML diagram editor, of course, right? No, that's not actually what we're going to do, right? Like, we're going to open up a text editor. And, I think we've seen a lot of text code on the screens today. And I think that's kind of an unquestioned assumption that most people have, that computer programs are written in plain text. Code is text. But that's not necessarily a given. It didn't have to be that way. So I thought for the final talk of the day, it might be fun to question this assumption a little bit and probe why things are that way. So, other formats, other complex documents are not necessarily text, right? Like if you try to cat a PDF in your terminal, it's gonna beep at you and print out lots of funny characters, right? And I'd say that computer programs are a lot more complex than a PDF, right? So why do they have maybe a simpler representation? There have been a lot of attempts actually over the decades to have non-textual forms of programming, and we're gonna dive into a few of those later in this talk. But first, I wanted to look a little bit at the history of text in computer programming, because I think it's actually somewhat more interesting than you might think. So, interestingly, it actually predates computers, which we're gonna talk about. So, as kind of a lens to dive into this, I wanted to, my first job, I was working at Google, and they, day one, they showed me, I was working mostly in C++, and they showed me their style guide, and I'd never seen a style guide for code before, and it said that every line you write has to be no more than 80 characters wide. And I thought that was kind of weird. I'd never worked with a line limit before. Sure, okay, I guess. But why did it have that rule? And I think line limits are somewhat controversial, but a lot of people work with these, right? So here's what C++ looks like. If you've ever never worked with it, you might want to have a few more characters in your line. But I wanted to focus on the cons here. So the 80-column limit is a hidebound throwback to 1960s mainframes. So what does that mean? I want to explore that phrase. Not so much the hidebound, which I think is a fun choice of adjectives, but more the 1960s mainframes. So, yeah, let's hop back in time. So, maybe the 1960s feel like a long time ago, but I'd just like to point out that we've seen a lot of JavaScript today, and the JavaScript era started in 1995 with Netscape Navigator. And, today, back to 1995 is the same as 1995, back to kind of the heart of the mainframe era. So for the people who are developing JavaScript back in the day, like maybe that was as relevant in their minds as, early versions of JavaScript are for you. So I think the mainframe era is still kind of influential today, maybe in slightly subtle ways. So has anyone ever worked with one of these before or know what this is? I see one hand, two hands, a few hands. Okay, I want to hear stories afterwards. So this is a punch card. So this was how computer programs were represented in the 60s and the 70s. So each punch card represented a single line of code. And there's some interesting aspects of this. So if you look at it, there's 3 rounded corners and 1 notched corner that helped you keep the orientation correct, so you couldn't flip it backwards. If you look at the very top, there's text written across. So z of 1 equals y plus w of 1. It's how you assign to an array element in Fortran. And each of these columns is a representation of that text in punches. And you have some statement numbering on the left and right as well. Of course, there's a JavaScript key punch emulator that you can go play around with. So, if you want to get like the authentic experience. But yeah, and there it goes. So there's here's the full character encoding, right? So this is every possible character you could write, at least in this version of the punch card. I guess a few things the thing I really want to point out here is this is not a binary encoding because there are physical constraints. You could not punch every single hole on a card because the card would lose structural integrity and it would jam up the card reader. And so the encoding was carefully designed to avoid having too many adjacent numbers, representing a character. So interestingly, like Z minus A was not 25 or 26. It was like 40, which if you've ever complained about ASCII or UTF-8, it could be worse. But, the reason this is relevant to our discussion is you can see on here that the columns are numbered, right? And how many columns are there? There are 80 columns. So that is the origin of the 80 character line limit. It's because of punch cards. There's some amazing hacks people came up with to make this stuff work. So each card is a single statement. So you would usually work with huge stacks of punch cards. And so I don't know if maybe it's 500 or 1,000 punch cards here. Basically everything you read or watch about punch cards, people talk about what a horrible thing it would be to ever drop a stack of punch cards. If you can imagine trying to reassemble a computer program from one line at a time. So the trick people came up with, other than the rubber band, is that red diagonal marker across the top. That's so that if you ever dropped it, it would be like a rough guide to getting things in the correct order. I also love that if you had a sequence of cards that did something in particular, you could just write in marker across the top what it did, right? So the cards at the top seem to be something to do with sorting. I don't know what skell is, but yeah, so that's maybe an early version of a comment, right? So this is the machine you would use with these. So the punch card reader is the blue and pink thing on the right, and the computer, the IBM 360, is on the left. That would be the thing that would actually run your program. And this was the only way to get a program into the computer, into its memory at this point, right? There was no screen on this computer. It would either print out its results on paper or on other punch cards. So this was truly non-interactive computing, right? This is like batch computing in its purest form. This is a key punch machine, so it's like a typewriter that you would use, and it knew how to do the encoding of the punch cards. What would happen if you made a single mistake in your 1,000 card stack, right? Like that could be catastrophic if you only found out a few weeks later after your program had run. So what these ladies are doing here is they are each independently keying in a computer program line, but that's was probably written out on a separate paper. They're keying it in line by line to create the punch cards, and then the machine in the back is a card verifier, so it's checking that each of their cards are precisely the same, and if they're different, it would reject them. So that was how you made sure you didn't have any transcription errors. So the punch card era, it was a long time ago, but I think it is actually still influential in some kind of subtle ways. So there's the 80 character line length limit, but also, especially if you've used some older programming languages, I think there's a tendency to have all of the commands be uppercase letters, like they were screaming at you, right? Like in BASIC, it was, print, like sub, go to. And that's a legacy of the punch card era because the character encoding space was pretty limited and you just didn't have lowercase letters. So everything was capital letters. So that's kind of a holdover from that era. I think we've mostly gotten over that. People seem to accept lowercase letters now. But cards had like an explicit area on the left for line numbers. So BASIC has explicit line numbers as well. That's sort of a more natural thing to do if that's where you're coming from. But I think the really interesting legacy is that like space truly was at a premium with these cards, right? Like it didn't really make a lot of sense to indent your code. You're just throwing away some of those characters. You didn't want to have really long function names because that would mean using many more punch cards. And so I think sort of this pattern that you sometimes see of people using cryptic short variable names and function names, I think that also is a legacy of the punch card era that we haven't totally gotten over yet. So we can keep diving backwards here. Why 80 characters? Why were the punch cards 80 characters? Well, the answer is it was an upgrade from the 45 column punch card, which was introduced in the 80 character card was introduced in 1928. So it was a natural thing to use when they first created computers. But like, if we didn't have computers, what would you do with a punch card? If you look really closely at this card, you might be able to guess. There's a lot of state names on the right of the card. But yeah, they were used for the US Census. So the 1880 census took about 8 years to add up all the numbers for it, which is sort of unsustainable, right? The census happens every 10 years. And so for the 1890 census, this fine gentleman here, Herman Hollerith, came up with a tabulation machine, which looked like this. And it would count which holes were punched in a punch card. And it could count up to 9,999. So I think that was what, each of the 4 dials looking up and down could show like 0 through 9. And so yeah, it could count up to 10,000. And this worked really well. There's some crazy physics about how this worked. I think the cards were put over a pool of mercury and there were like wires that physically went through them. It's just like unbelievable that this actually worked. But apparently it worked really well. So he started a tabulating machine company, which we know today as IBM. So that is the origins of IBM. But we can go back even farther. So this is a Jacquard loom. So the punch cards here are physically encoding the tapestry pattern. And these have been around for over 200 years. That's as far back as I know how to take it. Maybe I can go even farther back. You can let me know after the talk. Okay, so that was like kind of a interesting dive into the history of text. So I said we'd talk a little bit about some of the alternatives to text that people have tried over the years, because it really is a throwback. It's been around for a very long time. So this was an interesting one. Has anyone here used HyperCard? few more hands than punch cards. Yeah. So this made its debut with the Macintosh back in the 1980s. The quote I've heard about it was that it was everything before everything. It's sort of hard to categorize what HyperCard was using sort of modern categories of software. It was a little bit PowerPoint, a little bit Excel, a little bit IDE, a little bit web browser, because people just hadn't figured out, what those distinct tools were at that time. So it was a little bit of all of them. I thought this quote from Wikipedia was pretty funny about the origins of HyperCard. But this is like a sample of the sort of things that you could make with it. People made video games. People made what we would recognize as slides now. You could paint in it. So, the idea is that you would draw on a form, and then you would click on a button, and you could either make it go to a different card in your stack, or you could do some basic scripting in it. So if you double-clicked on a button, you could write something that looked a lot like AppleScript, if anyone has ever used that. So yeah, there's a lot of things from HyperCard that are still with us. So like the cursor, that how your cursor turns into a finger when you mouse over a link in a web browser, like that is a holdover from HyperCard. Like that's where that came from. And apparently the first wiki was also made in HyperCard. Visual Basic, this is another interesting one. Anyone use Visual Basic out there? Yeah, okay, a lot more hands on this one. Yeah, so came out in 1991, and similar idea. You have this palette of controls. You can draw on a form. You double click on a button, and then you can write code here. So this is you're writing in Visual Basic here. So I guess I should clarify what I mean about like non-text representations, because like clearly there's text, there's code here. So in both HyperCard and Visual Basic, there is some code, like some text, but the project as a whole, like kind of the highest level of organization, is not textual, right? And like if you save your Visual Basic program, it's not saving a text file. If you save your HyperCard program, you're getting a binary file. And that's the level at which you interact with it. You don't break that abstraction. Apparently Visual Basic is the origin of the phrase fire an event, which I hadn't really thought much about, but like makes zero sense. So there's a fun story about that if you want to read about it. The guy who created it liked to shoot rubber bands at his computer monitor when he was bored or like stuck. So fire a rubber band, fire an event. Yeah, it was quite popular. People did a lot of kind of internal, like in-house applications in Visual Basic, just because it was so much easier to spin up than a C++ Windows application. But it's sort of declined after like VB.NET came out, and it was much more like sort of normal programming. And I think it declined with the rise of the web in the early 2000s. All right, anyone used Interface Builder? Very few people. Interesting. So this was Apple, Next first, but then Apple. This is a similar idea, but had more of this model of like wiring up interactions between different parts of your program. So I thought this was an interesting idea, that you could actually drag from a control into your code to create a connection. That's mediated by this IB outlet, Interface Builder outlet. Spreadsheets. Anyone use Spreadsheets? Yeah. Okay. Great. Everyone's used Spreadsheets. Yeah. I mean, this is definitely a form of programming, of functional programming, even. The people do crazy stuff with Spreadsheets. They're more powerful than you might think. And I think they're probably the most successful. Well, I think with all of these non-text-based programming systems, part of the idea is to sort of bring programming to the masses, right? Make it more accessible. And I think Spreadsheets have probably been the most successful version of that. Like this is truly like bringing computation, the power of computation, to everyone. So I guess I should clarify, like, I think all of these systems have been quite successful in their own way, certainly Spreadsheets, but, looking at the all the code, all the programs that we've seen today, they are all still using text, right? And so I think, programming for building, large, like complex programs, we do all still use text. And that's kind of the thing that I'm trying to probe here. Yeah, there's been a lot of other things over the years. The original version of Netscape came with Netscape Composer. So in addition to the browser, it came with a composer. Oh yeah, people love this Brett Victor demo where you're like adjusting numbers in your program and you see the results. There's all kinds of interesting visualizations of code that are out there. So there's certainly been a lot of attempts over the years. But I think my sense of kind of why these haven't really taken over is that if you think about how computers work, there's just this huge tower of abstractions that we work on, right? Like there's atoms at the very lowest level. That's the most real thing. But then, going up from there, you have transistors, circuits, CPUs, and then, we have machine code. And eventually we get up to the code that we work with on a day-to-day basis. And I think that generally we always wind up working at kind of the highest level on this stack where things can go wrong, right? So, you generally are not going to have to debug things at the level of like transistors or circuits. Like, I really hope not. Compiler authors in the audience will probably disagree, but like generally, compilers work. And if you have a bug in your program, it's that bug is also manifest in the source code of the program. So you typically can debug problems at the level of your source code. But I think the risk if you go higher up in this stack to things that generate code, for example, or these visual editors, is that typically that next step winds up being a leaky abstraction. And I think this is a super useful concept to have in the back of your head. So if probably a lot of people in this audience are familiar with the concept, but if you're not, I want to go through maybe my favorite example of what turns out to be a leaky abstraction. So has anyone used GWT, the Google Web Toolkit? A few people. Yeah, I mean, it's an amazing piece of engineering, but well, okay. So, let's go back in time to 2006. So, you have a client, you have a server, you really want to share code between these two things because, like, wouldn't that be great to just work in one programming language? And, since it's 2006, like, we're probably going to be writing our server in Java. So, wouldn't it be great if we just didn't have to, yeah, you guys remember Java? It's great. So the idea was that, 2006 JavaScript kind of sucked. Like, wouldn't it be nice if we could pretend that that JavaScript didn't exist, that wasn't a thing? So the idea with GWT is that you write your client-side code in Java, and GWT compiles your Java to JavaScript, and the JavaScript runs in the browser. And so you can just work in Java. You only need to know Java. You can share code between your client and your server because everything's Java. And yeah, you can just forget about this whole JavaScript thing. Great, right? So anyone remember this? Google Wave was a famous user of GWT. So the problem with this is that if you once you started using GWT, it turned out if you needed to debug things in the browser, you actually kind of did still need to know JavaScript, and you also would sometimes run into bugs with the translation layer. So you really needed to know GWT pretty well, and then of course you also needed to know Java because that's what you were writing things in the first place. And so, we kind of had this like classic XKCD problem, right? Is like, you think you're going to introduce this new thing to consolidate everything onto like one standard, but in fact, you just have like created a new thing that everyone needs to know, right? So it's a leaky abstraction because the idea is that you only need to think about one thing, but in practice, you actually need to think about three things. So it's not really saving you the effort. I think people still use GWT. I'm not totally sure, but and I'm sure it still has its uses, but this is kind of I think why it hasn't really taken over. The other reason, of course, being that we came up with a slightly different way to share code between client and server, which I think for people who are not developing JavaScript in 2006, it's hard to understand how incomprehensible the way we do coding is now, just given where JavaScript's reputation was. Just the idea that we would achieve code reuse between client and server by writing our servers in JavaScript. I think if you could go back in a time machine and try to convince someone in 2006 that was what we were going to do, like they would not believe you. But that's kind of how it's gone, and it basically works. I think there's been a lot of incredible tools that have come out since then that have really facilitated this. I think V8 was probably the main enabling one, and then with newer versions of JavaScript, the language itself has gotten a lot better. So I think these visual editors tend to be examples of this as well. So if you think about something like a WYSIWYG HTML editor, like you can edit, or like CSS, you can edit things visually, but then inevitably once you start trying to do something a little bit more dynamic, a little bit off the beaten path, you're gonna have to go one level lower to make that work. And then suddenly things have gotten out of sync, and maintaining this higher level abstraction becomes work for you. And I think at that point, you are going to have to work at the lower level, the level of code anyway. And so I think inevitably that winds up being the level at which you'll work. So, it's worth saying that like text is not the final representation of your program, right? Like it goes through a lot of transformations from text before it finally gets executed. But I think, things like, your text gets converted into a syntax tree, and then it gets compiled down to either bytecode or machine code, or just interpreted. But generally, that process is complex, but I think it is generally pretty well understood. And it, compiler authors tell me I'm wrong, but mostly it works. Like I said, usually if you have a bug in your program, it is not a compiler bug. Hopefully it is actually a bug in the text of your program, and that's a level at which you can debug it. So I think another good reason that we use text is that there's great tooling for text, right? So if you imagine doing like development in a spreadsheet, how would you diff a spreadsheet that's stored in a binary format or like a HyperCard stack? Like text, we have lots of great diff tools, right? But if you use some sort of binary format, then you're probably going to be dependent on whoever, the vendor who produces that environment to provide their own diff tool, which, they may or may not do, and you're probably stuck with that one. Whereas text, we have all the great tools we know already. Merge conflicts, right? Like how would you resolve a merge conflict in a HyperCard stack? I don't know. Merge conflicts aren't super fun to resolve, but at least we have tools to help us do that with text. So, and I think another great thing about text is just that the barrier to building new tools is really low, and so we get lots of great new tooling with text. So yeah, like could this shift? So I think in a subtle way it kind of has over the last 10 or 15 years. So this is going to be a little mathy, but if you think about a compiler as, part of it is going from the text of your program to an AST. A formatter goes from an AST to text. And so in math, if we have these two mappings, we can put them together and get this bidirectional mapping. And if you have a bidirectional mapping between two things, then in math, at least, you would say they're equivalent. So on some level, if we all are using auto formatters, then in some sense, we are actually like operating on the AST, right? Like the individual characters in our code are kind of an artifact that we don't really need to think too much about. I think it's kind of fun to talk about the rise of these auto formatters. If people don't know this history, I think Go was really the pioneer here with the Go formatter. So they took a very hardline stance that if your code wasn't formatted with the Go formatter, then it didn't compile, which seemed like crazy in 2011, but I think it's actually like stood up pretty well. And the reason is that we used to, when people did code reviews, we used to have these like horrible arguments about white space and indentation and formatting and line breaks. And it turns out those are all just a waste of time, you know? Like I might not always agree with Prettier's formatting choices, but like I'm much happier to just accept those and not have horrible discussions about white space. So that's kind of the history of that. Yeah, it's 2024, right? We should talk about AI. So I've seen lots of people who are excited about having, you write your code and like no one likes writing unit tests, so I'll just have AI generate my unit tests for me. But I actually think going the other way around is more interesting, where you write your unit tests and then you have AI generate your implementation for you, right? So that's like true like terrifying test-driven development that, if you haven't encoded a behavior in the test, then like how is the AI ever gonna encode that behavior? I think if you think about that hierarchy of the different levels at which we can operate, I think AI it's never going to be 100% right. And I think you are inevitably going to have to debug the code that it generates. And so I think I'm not convinced that this is actually going to like fundamentally change the level at which we operate with code. I think we are still going to have to work with the text. So that's kind of why I think we work with text. I think it's actually it's a pretty good level of abstraction at which to operate. It it lets us debug our problems at that level, and it lets us get really great tooling. So I think text is going to be with us for a long time to come. Thanks.
Thanks, Dan.
Shall we head to the interrogation booth?
Please, after you. Okay. So there is one very important question. There's several questions. One is more important, and that is, how many punch cards for checker.ts?
Well, what did we hear earlier? It was like 50,000 lines. So I don't know what like millimeter thickness each of those punch cards were, but hopefully it would be less wide than this screen up here.
Another question. What do you think the main challenges are with the goal of generating bytecode from straight AI-based tools, instead of currently how it still needs to write out human-readable code as an intermediary step?
Yeah, I mean, I think it's kind of what I was saying about like you really want to, in order to forget that a level of that stack exists, like you really need it to work almost 100% of the time, right? So like if you think about all the bugs that you've run into in your career, like how many of them turned out to be CPU defects? Like probably zero. Like if you work at a huge company and someone actually finds out that like a production bug was caused by a CPU defect, like everyone gets excited about that because it's so unusual, right? And maybe compiler bugs are a little less rare than that, but it's still very rare that you would run into one of those, or like you run it, your program fails because of a bug in Node, right? It's almost always a bug in your own code. And so I think if we ever get to a point where AI can generate code like that reliably, but I'm just so skeptical that we're going to get to that point, because like if you think about telling another person what you want a program to do, like there's inevitably ambiguity in what you're asking of it, and you're going to run into problems. And I think as soon as that happens, you're going to have to get into the code and figure out what's going on.
And we are out of time, but there are a lot of great questions. And one bit of follow-up. I did the math on 20 weight paper. 50,000 lines would be 66 feet tall. So just taller than
the screen, but not quite as wide.
And just real quick for fun, what's your favorite Unicode character?
My favorite Unicode character? Oh man, I don't know. Maybe a fish, since we're at the aquarium. Yeah. Or we saw some lovely seals over there just now. So I don't know if there's a seal Unicode character.
Nice. Well, thank you so
All
much,
right,
Dan.
thank
Let's give him a
you.
round of applause.